In the previous topic, we went over two different configurations, the parallel plates and the dipole configuration, and we examined how the equipotential lines and the electric field lines would vary from one configuration to another. Whereas in today's topic, we are going to be introducing the notion of capacitance, and more specifically the capacitance of a parallel plates capacitor. So basically we are going to be focusing our study on the first configuration of last week, which is the parallel plates capacitor. But we are going to focus on it mainly in terms of capacitance. In addition, we are going to study the effect that a dielectric has on the capacitance of that capacitor. So first off, what's a capacitor and how does a capacitor actually work? A capacitor is defined as a device, as an electrical device that consists of two parallel conducting plates. So whenever you have two conducting plates that are disposed in such a way to be parallel to each other, therefore the combination of these two plates would form a capacitor. And the capacitor, in that case, it works by building up opposite charges on its parallel plates. But how does such process actually work? How can a capacitor acquire positive charges on one plate and negative charges on the other? Let's have a look at the following circuit, which consists of a battery that is connected across the parallel plates of a capacitor. So the positive terminal is connected to the upper plate and the negative terminal is connected to the bottom plate. And in between these two plates over here, we actually have an insulator, which is none other but free space. Now initially, if the battery is at 0 voltage, therefore we don't have any buildup of charges on these parallel plates, meaning that neither plate is going to be acquiring positive or negative charges. Now let's say that we start to slowly increment the voltage that is being supplied by the battery until it reaches its maximum at 1.5 volts. So as we keep incrementing the voltage, if we look below at that bottom plate, we can see that the bottom plate is acquiring more and more negative charges. So with every increment in voltage, the amount of electrons that are residing on that bottom plate is actually increasing. And in a similar manner, the opposing plate is also acquiring more and more positive charges. So what's happening in that case? Let's lower the voltage back to 0 and then we increment it again. As we are incrementing the voltage, if you look at the wire below, the wire which is connected to the negative terminal, we can see that we have a blue arrow. That blue arrow is the direction of what? It's a direction of the electrical current. And we know that the electrical current is none other but the direction of the moving electrons. So it's basically the flow of electrons. So in that case, the electrical current or the electrons, they are coming out of the negative terminal, moving around and entering into the positive terminal. However, in our case, these two plates are separated by an insulator. So these electrons, they cannot traverse all the way into the positive terminal. But instead, what's happening that these electrons, they are actually residing on the bottom plate. So once you have electrons residing on that bottom plate, by induction, the opposing plate is going to be releasing electrons. So let's have a look again. As we are incrementing the voltage, if you look at the upper wire, which is connected to the positive terminal, we can see that we have a blue arrow. That blue arrow is an indication of the electrons that are being released by the upper plate. So whenever the bottom plate is acquiring electrons, the upper plate is going to be releasing electrons. And for every electron that is being released, it is going to leave behind it a positive hole. A positive hole meaning a positive charge. So in that case, eventually we are going to have a buildup of negative and positive charges on these parallel plates. And that process of storing charges in these plates is going to keep happening until we reach the maximum voltage between these two plates, which is going to equal the voltage of the battery. So the process of storing charges in these two plates would keep going on until the potential difference between these two plates is equaling the potential difference of the battery. So in that case, if we bring a voltmeter in order to measure the potential difference between these two plates, we can see on the screen of that voltmeter that the potential difference in here is actually equal to the potential difference that is being supplied by that battery, which is of 1.5 volts. So as we have just seen, the amount of electric charges that are stored in a capacitor is directly influenced by the amount of voltage applied. So whenever you increase the amount of voltage applied, therefore the amount of charges stored in a capacitor is going to increment. And mathematically that relationship between Q and V is given as Q equal to C times delta V, where Q and delta V are directly proportional to each other. So whenever you increment the amount of voltage applied, therefore the amount of charges stored is going to increment as well. Now what about that C over here? That parameter C is a positive proportionality constant, meaning it's a positive proportionality constant between Q and delta V. And that proportionality constant, we label it as the capacitance. So what's the capacitance? What does it signify physically? The capacitance, which is equal to Q over delta V, so the capacitance, which is equal to Q over delta V, is none other but a measure of storing electric charges for a given voltage applied. So it's a measure of storing electric charges for a given voltage applied. So basically the definition is none other but that ratio, Q over delta V. So the capacitance is none other but the measure of storing electric charges for a given potential difference applied. And the unit of capacitance in that case would be farad. So for example, if you consider 1 farad can be equal to, for example, 1 coulomb per 1 volt applied. So 1 farad in that case, it implies what? Or it represents what? It represents the capacity of storing 1 coulomb of charges per 1 volt applied. For example, if you had 1 farad equal to 8 coulombs per 8 volt, therefore it represents also the capacity of storing 8 coulomb of charges per 8 volt applied. So far we have seen that the amount of charges stored in a capacitor, it can be directly influenced by the amount of voltage applied. Now besides the potential difference or the electric potential applied being a direct contributor to the amount of charges stored in a capacitor, there are also other factors which can impact the amount of charges stored in a capacitor. So what would be these factors? These factors are the separation between the plates and the surface area of the plates. So over here between these two plates we have a certain separation D, and each plate has a certain surface area A. Of course, that area is going to be the same for both plates. But how can we relate between the capacitance of that capacitor and its surface area and the separation between its plates? So what we need to do next is we need to establish an equation, a relationship, which is going to relate the capacitance to D and to the surface area. Let's consider the following two parallel plates. So one plate is acquiring positive charges and the other plate is acquiring negative charges, and between these two plates we have a certain separation D, and each plate has an area A. So previously we have established the equation Q equal to C times delta V, which is a relationship relating the amount of charges stored to the potential difference applied. So over here we are going to suppose also that we have a certain battery connected. So we have a battery connected to these two parallel plates. Now in the previous example, or in the previous experiment, we saw that whenever you have a steady current or a steady voltage applied to the plates of a parallel plates capacitor, therefore on each plate we are going to have a uniform distribution of charges. So on that plate we have a uniform distribution of charges, and on that plate we have a uniform distribution of charges. Therefore the electric field which is going to exist between these two plates is going to be a uniform electric field. So over here everywhere we have a uniform electric field directed from positive to negative. And we also saw in the previous experiment that the electric field in that case is given as delta V equal to the electric field times the separation, or the electric field between these two plates is equal to the potential difference between these two plates. So delta V would correspond to the potential difference, delta V over the separation. So in that case, that equation over here becomes Q equal to C times the electric field times the separation. Therefore, the capacitance is equal to the charges over the electric field times the separation. So now in that equation over here we have an unknown, which is the electric field. We need to determine an expression for that electric field. How can we do so? In order to determine an expression for that electric field, we are going to revert to Gauss' law. So what is actually Gauss' law? Gauss' law is basically the study of the electric field that is being generated by electric charges. So Gauss' law consists of considering a certain Gaussian surface, and that Gaussian surface is basically a fictitious, a closed surface in three-dimensional space. So first off, we are going to start by considering a certain fictitious surface in three-dimensional space. However, that Gaussian surface, it must have a very specific geometrical shape. So we are going to consider over here that we have the following cylinder. So as we can see, the bottom part of the cylinder is located on that positive plate, while the other parts of that cylinder are actually located in free space. So we are going to refer to that cylindrical shape over here as the Gaussian surface in three-dimensional space. So that cylindrical surface over here, we are going to refer to it as a Gaussian surface in three-dimensional space. Moreover, like I said before, the bottom part of that Gaussian surface is actually located on the positive plate. So that circular part over here is going actually to be enclosing within it, meaning it's going to be confining within it a certain amount of charges. So over here, within that circular part, we are going to have certain amount of charges confined within it. And we are going to refer to these amount of charges as Q prime enclosed, meaning that we have a certain amount of charges of Q prime that are enclosed in that circular part. Moreover, let's consider that that circular part, it has a certain area A prime. So A prime would be the area of that circular part which is located on that plate. And like I said before, the other parts of that cylindrical Gaussian surface are actually located in free space, therefore they are not enclosing any charges. Now the fact that we have charges enclosed in that circular part over here, therefore we know from previously that an electric charge is going to produce an electric field. So over here we have multiple electric charges enclosed in that circular part, therefore they are going to generate an electric field flux. So through that Gaussian surface, we are going to have the following electric field flux moving through it, and that electric field flux is basically generated by Q prime enclosed. And we need to determine an expression for that electric field flux. Mathematically, the electric field flux through a given area is given as, so the electric field flux through a given area is given as a closed integral of E dot dA is equal to Q prime enclosed over epsilon 0. So that would be the general equation for Gauss' law, which consists of a closed integral of E dot dA equal to Q prime enclosed over epsilon 0. There are two things over here that you need to keep in mind. First off, that electric field is directly proportional to Q prime, which is logical because the electric field is actually produced by an electric charges. So E and Q prime, they are directly proportional to each other. Moreover, over here we are multiplying the electric field by a surface element, because that surface element is going to be enclosing a certain amount of charge. and therefore that electric field is going to be generated by that surface element which is enclosing a certain amount of charge. Because if you go back to that definition over here, the electric field flux, we are finding the electric field flux through a given area, which is generated by a given area which is enclosing a certain amount of charges. Now you might ask why we are taking over here a surface element and not the entire surface. Because in that case, once you are able to find the electric field that is generated by a surface element, therefore you would be able to integrate that surface element from 0 up to A prime. Therefore in that case you would be able to integrate the A from 0 to the entire area of that entire circle that is residing on that plate of the capacitor. Now moreover, we have said before that on each plate we have uniform distribution of charges. Therefore the electric field between these two plates is actually uniform. So E over here is a constant. So we can take it out of that integral. Therefore that equation becomes E times the integral of dA, where like I said the A is going to be integrated from 0 up to A prime, where A prime would be the entire area of that circle which is enclosing a certain amount of charges Q prime, is equal to Q prime enclosed over epsilon 0. Therefore that becomes E times A prime. Now you might say that why don't we replace A prime with pi r squared? It is not needed in that case. We don't need to find the area of that circle, but rather we only want to have a certain notation for it. So E times A prime is equal to Q prime enclosed over epsilon 0. Therefore the expression of the electric field becomes E equal to Q prime over A prime times epsilon 0, and therefore the previous expression for the capacitance becomes C equal to Q over E times D, which is equal to Q over Q prime times the separation times A prime times epsilon 0. Now that final expression for the capacitance, there are still two parameters that we need to get rid of, which are A prime and Q prime. How can we do so in that case? If we go back to that sketch over here, we said before that we are considering that these two plates are actually subjected to a steady voltage. Therefore we have a uniform charge distribution on each plate. And since we have a uniform charge distribution, therefore we have the same charge density everywhere on each plate. The charge density is basically the amount of charges that are present per unit area. So over here, whatever surface area that you pick on that surface plate, you are going to have the same charge density everywhere, whether you pick that entire plate or whether you pick that circular part over here, which is part of that Gaussian surface. So in that case, the charge density is given as Q over A. So like I said, for that entire plate we have the same charge density everywhere, which is Q over A. Therefore Q is equal to sigma A. And moreover, if we actually choose that circular part over here, which is part of that Gaussian surface, it also has the same charge density as the entire plate, since we have a uniform charge distribution everywhere. Therefore sigma is also equal to Q prime over A prime for that circular Gaussian surface. Therefore Q prime is equal to sigma A prime. So now we have these two equations over here that we are going to fill in the equation above. Therefore the capacitance becomes C equal to Q, which is sigma A. So we have Q is equal to sigma A times A prime times epsilon 0 over Q prime, which is sigma A prime times the separation. So now we can simplify. We have A prime in the denominator and A prime in the numerator. Also over here we have sigma and sigma we can get rid of. And finally we are left with that the capacitance is equal to A times epsilon 0 over the separation. And that would be the final expression for the capacitance, which, as we can see, it is actually dependent on the surface area of the plate. And then over here we have the separation between the plates, and over here we have the permittivity of free space. So the capacitance is basically directly proportional to the surface area, meaning that in order to increment the capacitance of a capacitor, you have to use plates of a bigger surface area And C is also inversely proportional to D, meaning that in order to increment the capacitance, the separation between these two plates has to be very narrow. So the narrower the separation is, and the greater the surface area is, therefore the greater the capacitance for that capacitor is going to be. Now that equation that we have established over here is in the case where you have a free space as an insulator between these two plates. So over here basically we have free space as dielectric between these two plates. And for free space it has a certain dielectric constant which is K equal to 1. So over here in that case, that capacitance that we have found, it is actually specific for free space as a dielectric. So in that case we are going to generalize that equation in order to include any other dielectric that we might have between these two plates, and therefore the expression becomes C equal to K times A times epsilon 0 over D. So what would be the dielectric constant in that case? The dielectric constant is basically, it's a ratio between the capacitance of a capacitor whenever it has a certain dielectric placed between its two plates with respect to the capacitance of a capacitor when it has a free space as a dielectric. So K is basically C dielectric over C free space, meaning it's the ratio between the capacitance of a capacitor whenever it has a certain dielectric placed between its two plates with respect to the capacitance of a capacitor which has free space as a dielectric. So whatever value you obtain for K is basically showing you the factor by which the electric field is dropping with respect to free space whenever you place a certain dielectric between the plates of a capacitor. So over here, that general equation that we have defined, it is basically dependent on K, which is dielectric constant. So for example, if you have free space as a dielectric constant, therefore simply you can equate K to 1 and you can get rid of, and therefore C would be equal to A epsilon 0 over D. Now regarding the purpose behind the dielectric, why do we actually use a dielectric in that case? How can a dielectric affect the capacitance? We already know that the dielectric is basically an insulating material, meaning it's a material that cannot exchange charges with any other object. And the dielectric, it consists of polar molecules, meaning molecules that have both polarities, negative and positive. So when the dielectric is not placed near a charged object, therefore these molecules, as we can see, would be actually distributed in a random manner. However, what would happen if you place that dielectric between two charged objects? So for example, let's say that we are placing the dielectric between the parallel plates of a capacitor, between two charged plates of a capacitor. So the moment you place the dielectric between two charged plates, as we can see, it is going to get polarized, meaning that the negative molecules, not the negative molecules, but the negative part of a molecule is going to be attracted toward the positive plate, and the positive part of the molecule is going to be attracted toward that negative plate. Therefore, that would render our dielectric polarized, meaning that now it has a positive and a negative polarity. Now, the fact of polarizing that dielectric over here, the fact of having negative charges lined up near the positive plate, and the fact of having positive charges lined up near the negative plate, that is going to negate the effect of some of the positive charges and some of the negative charges, meaning it is going to render the effect of some of the positive and the negative charges ineffective. And this is going actually to lead to a decrease in the potential difference between the plates of that capacitor. So over here we have a lineup of negative charges near that positive plate. Therefore, that lineup is going to cause the effect of some of the positive charges negligible, meaning that it is going to render them inert, ineffective. And this is going to lead to a drop in delta V. And in a similar manner, these positive charges over here, they are going to lead to a negation of the effect of some of the negative charges. Therefore, they are not going to be contributing to the voltage anymore, and this is going also to lead to a drop in delta V. But over here you have to keep in mind one thing, that despite the fact that we are negating the effect of some of the positive and the negative charges, these charges are going to remain on that parallel plates capacitor. So Q so far is not changing. The amount of charges stored so far is not changing. Now, one thing to keep in mind that you can also think of that negation in terms of an opposing electric field. So these two parallel plates, they already have their own electric field, which is directed from positive to negative. Then, after getting that dielectric polarized, now it's going to have its own internal electric field. Let's call it E prime, which is directed in the opposite way of the initial electric field of that capacitor. So that opposing electric field is going to cause a negation in the effect of some of the positive and the negative charges, which is going to lead eventually to a drop in delta V. But keeping in mind that Q so far is remaining a constant. Now when it comes to the battery is not going to be aware of all of that. It's not going to be aware that these charges are still remaining on that plate over here, but rather the battery is going to notice that we have a drop in the potential difference between these two plates. And the role of the battery in that case would be to try and to bring the potential difference between these parallel plates back to its maximum. So now the battery is going to be supplying both plates with more charges in order to bring its potential back to its maximum value. Therefore, that battery is going to keep supplying these two plates with more and more charges. Therefore, Q is going to increase, and Q would keep incrementing until we reach the condition where delta V, or the potential difference between these two plates, is now equal to the potential difference of the battery. So in that case, we know that C is equal to Q over delta V. So while delta V is remaining a constant due to the presence of the battery, and while Q is incrementing in order to keep delta V equal to V at all times, therefore the capacitance of that capacitor is going to increment. So what would be the role of the dielectric in that case? Whenever you place a dielectric between the parallel plates of a capacitor, the capacitance is going to increment, because from one side the battery is going to keep supplying these two plates with more charges in order to keep the potential difference equal to the potential of the battery, and therefore the Q is going to increment as a result, and finally the capacitance of the capacitor is also going to increment as well. Now what would happen if we didn't have a battery? So let's say we don't have a battery in that case, but we have a dielectric placed in the middle. Of course, dielectric is still going to get polarized. So over here we have the polar molecules being polarized. And moreover, these polar molecules, or the alignment of these polar molecules, is going to negate the effect of some of the positive and some of the negative charges. So as a result, the potential difference is going to drop. However, this time we don't have any battery in order to bring that potential difference back to its maximum. Therefore, C, which is equal to Q over delta V, it depends on Q and it depends on delta V. Now when it comes to Q, Q is going to remain the same. So like I said before, even if you negate the effect of some of the charges, these charges are going to remain present on these two plates, but their effect is actually rendered negligible. Therefore, delta V is going to drop, Q is going to remain a constant, therefore C over here is going to increment. So as we can see, C and delta V, they are directly proportional to each other, so whenever delta V drops, Q is remaining a constant, therefore the capacitance of that capacitor is going to increment as well. But that would be in the case where you don't have a battery connected to it. Now what would happen to the electric field in that case? We have seen before that the electric field is given by delta V is equal to E times D, so the electric field is given as delta V over D. So the electric field, it mainly depends on that potential difference. Now what would happen in that case, in the first case over here? And of course we are referring to the electric field which is generated between these two plates. So for that first case, as we have seen, that the presence of the battery, it kept that potential difference over here a constant. It kept the potential difference between these two plates equal at all times to the potential difference of the battery. Therefore, for the first case, that electric field is going to remain a constant. It's not going to change, since delta V over here is held a constant by the presence of the battery. Now in that second case, we don't have a battery in order to supply a capacitor with more charges in order to keep its potential difference at its max at all times. Therefore, in the second case, delta V is dropping. So whenever delta V is dropping, and since the electric field is proportional to delta V, therefore the electric field is going to drop in that case as well. Let's have a look at the following circuit which we have studied before, which consisted of a battery supplying two parallel plates with charges until the potential difference in between these two plates reached the potential difference of the battery. Now let's say that we bring in a dielectric material. So initially the dielectric material is not polarized. So as we can see, the negative and the positive sides of a polar molecule, they are actually balancing each other out. Now let's insert the dielectric material in between these two plates. As we can see now, the number of charges on the plates, they have incremented drastically, and also the capacitance above, if you have a look at the capacitance is also incrementing drastically. But moreover, if you look at the dielectric, now the dielectric, it has become polarized, meaning that the negative plate, the negative side of a polar molecule, they are attracted toward the positive plate, and the positive side of the polar molecules are attracted toward the bottom plate, which is the negative one. But the thing that we have noticed is that the positive charges on that upper plate, they have incremented drastically. And that is due to what I have told you before, that whenever you insert a dielectric in between two charged plates, that alignment of negative charges above is going to negate the effect of some of the positive charges. Therefore, they are not going to contribute to the potential difference anymore. So the potential difference is going to drop. And in a similar manner, that alignment of positive charges below is also going to negate the effect of some of the negative charges on the bottom plate. So they are going to be rendered ineffective, and therefore that is going to lead to a drop in the potential difference. So in that case, the aim of the battery is going to be to try to increment that potential difference in between these two plates back to its maximum, back to 1.5 volts. Therefore, it's going to be supplying the plates with more and more charges. And that is why over here we are actually noticing an increase in the positive charges. Because right down below, we also have an increment in the number of the negative charges in order to make up for the ineffective charges that were actually rendered ineffective by the presence of that dielectric. Therefore, by incrementing these charges on each plate, we have actually incremented the potential difference in between these two plates back to 1.5 volts. So if you bring a voltmeter, and we connect it across the plates of that capacitor, we can see that that voltmeter is actually reading a value of 1.5 volts, which is none other but the value of the main voltage that is being supplied by the battery. In addition, if we have a look at the plate charge, so let's try and have a look at the number of charges in before we insert the dielectric material. So in before we insert the dielectric material, the total number of charges, it was 1.33 times 10 to power negative 13 coulomb. And then after we have inserted that dielectric material, the number of charges on these two plates, it kept on incrementing until it reached a maximum of 6.64 times 10 to the negative 13 coulomb. So as we can see, the presence of a dielectric, it incremented the number of charges that are present on each plate. And that would be due to the fact that the battery is actually supplying these two plates with more and more charges in order to bring up the potential difference to 1.5 volts.